Radar systems are kind of like the invisible senses of our modern world. I mean, they're absolutely everywhere, guiding airplanes, keeping our cars safe on the road, and even monitoring the weather. But here's the thing, not all radar is created equal, not by a long shot. So let's dive in and break down the different types of radar, see how they work, and figure out where you encounter them in your everyday life. So let's start with a simple question. How does a modern car's safety system, see a pedestrian in the pouring rain or in complete darkness when a camera would just be totally lost? Well, the answer, of course, is radar. And this is one of the most common and frankly critical uses of the technology we're about to explore. Okay, so before we get into all the different flavors, let's just nail down the basics. Radar. It's actually an acronym. It stands for radio detection and ranging. And at its heart, it's a system that uses radio waves to figure out where things are, how far away they are, and how fast they're moving. Simple as that. And how does it do that? Well, it's really a pretty simple process at its core. First, it shoots out a wave of electromagnetic energy. Second, that wave hits an object and bounces back. And third, the radar's antenna picks up that reflected signal, the echo. It's in that final step, analyzing the echo, where all the magic happens. That's where the system pulls out all that crucial information. And this basic principle, it applies to every single radar we're going to talk about today. All right, now that we've got the fundamentals down, let's look at the two original pillars of radar technology. Think of these as the OGs, the foundational building blocks that pretty much everything else is derived from. First up is pulse radar. This is the classic radar you're probably thinking of, right? Like in old war movies. Its job is simple. Find out how far away something is. It sends out a short, really powerful pulse of energy, and then it basically starts a stopwatch. The moment the echo returns, it stops the clock. By measuring that round-trip time and knowing the speed of light, it can calculate the distance with incredible accuracy. The concept is simple and super effective for long-range detection, but it does require a big, big blast of power for each pulse. The second pillar is continuous wave radar, or CW radar. Now, unlike pulse radar, this one doesn't send out short bursts. Nope, it transmits a constant, continuous signal. It's not listening for a time delay. Instead, it's listening for a change in frequency. And this is the famous Doppler effect in action. If an object is moving towards the radar, the frequency of the wave that comes back is higher. If it's moving away, it's lower. This makes it absolutely perfect for measuring speed. Think of a police speed gun. But it's got one big catch. A basic CW radar can't tell you how far away the object is. So, when you put them side by side, it really spells out the fundamental trade-off of those early radar systems. You had pulse radar, the rangefinder, which used time delay, and then you had CW radar, the speed detector, using the Doppler shift. For a long, long time, you basically had to pick one or the other. Well, that naturally leads us to the next stage in radar's evolution. You see, engineers faced a really clear challenge. How do we get the best of both worlds? How can we build a system that measures both how far away something is and how fast it's moving all at the same time? This is where things get really, really clever. Let's just ask the question directly, because this is the exact problem that drove all the innovation forward. I mean, think about an advanced driver assistance system in a car. It absolutely needs to know both the distance to the car in front of it and its relative speed to make a split-second safety decision. So, how'd they solve it? Enter FMCW, or Frequency Modulated Continuous Wave Radar. This is a game changer. Instead of a constant frequency, FMCW sends out a signal whose frequency actually changes over time. We call this a chirp. So the time difference between when the chirp goes out and when its echo comes back gives you the range, just like a pulse radar. But, and this is the brilliant part, the frequency difference between them is because of the Doppler effect, and that gives you the velocity. It's an incredibly efficient all-rounder, which is why it's a cornerstone of modern automotive radar. Another powerful solution is pulse Doppler radar. This one takes a different approach. It uses the pulse method to find range, but then it also analyzes the frequency of those returning pulses to get the Doppler information for velocity. Its superpower, though, is its amazing ability to filter out clutter. It can look at a whole scene, identify all the non-moving background objects, things like buildings or mountains, and just erase them, showing the operator only the moving targets. This is absolutely critical for things like air traffic control and military applications. Okay, so we've covered radars that can measure range, speed, or even both. Let's move on to the next frontier, because the newest advancements aren't just about what is measured, but how the radar actually looks at the world. And it does this using some incredibly sophisticated antenna technology. So check this out. This is a phased array radar.
Instead of one big rotating dish, it uses a grid of many small stationary antennas. By precisely controlling the timing of the signals sent to each of those tiny antennas, it can make the waves add up in just the right way to form a really focused beam. And by just adjusting that timing, it can steer that beam electronically, almost instantly, in any direction. No moving parts. That means it's incredibly fast, reliable, and versatile. This is the tech behind advanced military radars, and believe it or not, it's a key concept in how 5G networks create focused beams to give you faster data on your phone.
And if we take that idea even further, we get MIMO radar. That stands for multiple input, multiple output. Just like the name suggests, you're using multiple antennas to transmit and multiple antennas to receive. So each combination of a transmit and receive antenna creates its own unique path through space. By processing all of these paths together, the system creates a virtual antenna array that's way larger than the physical device. This gives it a much more detailed, high-resolution view of its environment. It's like going from a single pixel to a full HD image. This is a total game changer from next-gen automotive radar. And finally, we have one of the most ingenious types, synthetic aperture radar, or SAR. So imagine you want to create a super detailed image of the Earth's surface from space. You'd need an antenna hundreds of meters wide, which is pretty much impossible to launch. SAR solves this brilliantly. As a satellite or a plane flies along, it takes a bunch of rapid radar snapshots from different positions. It then combines all of this data to synthesize a massive virtual antenna. The result? Stunningly high-resolution images, day or night, whether it's cloudy or clear. So, wow, we've covered a lot of ground, from the basic pillars to the mind-bending advanced stuff. Now, let's just take a moment to tie all of these concepts together and see how they form the backbone of technologies that we rely on every single day. This summary table here is the perfect cheat sheet. You can literally see the evolution right down the columns. We started with pulse, which measures range using time delay, and CW, which measures velocity using Doppler. Then we got the hybrids, like FMCW and pulse Doppler, which measure both. And finally, we get to the advanced systems, phased array, MIMO, and SAR, where the key feature isn't just a simple measurement anymore, but a whole new capability, like beam steering or high-res imaging. And this is where it all comes home. That clever FMCW radar we talked about, that's what's running your car's adaptive cruise control and emergency braking. That phased array concept of beamforming, it's a critical part of how 5G gives you a stable, crazy fast connection. And MIMO? Well, MIMO is blurring the lines between communication and sensing, and it's powering the next wave of smart devices.
So, what are the big things to take away from all this? First, there's no one-size-fits-all radar. These are highly specialized tools built for very specific jobs. Second, if you really want to understand the technology that's shaping our world right now, you have to get a handle on FMCW and MIMO. And finally, the lines are blurring. The principles of radar and wireless communication are starting to merge, and that's creating some incredibly exciting new possibilities for the future. And that leaves us with a final thought to chew on. As we build more self-driving cars, more automated drones, and smarter cities, we are relying more and more on these systems to be our eyes and ears. So the question is, which of these remarkable technologies, these invisible senses, will end up becoming the most critical to our automated future?